So if you turn to your modules, okay, if you turn to your modules, I asked you to do this to prepare for today's class. So I hope that you guys have done it. Because if you guys haven't done it, then it will be a very huge waste of time. Okay, so we are looking at question number 3, question number 4, and question number 5. Okay, with the exception of the graph. Right. So so far we have studied the interference patterns. Okay, in a water wave, and we can use actually the same principle when we later look at light waves and also sound waves. Okay, and when we look at water waves, we understand that there are three very important letters lah. Okay, the first letter is the letter A. Okay, and the letter A stands for the distance between these two wave sources. Okay, dia punya sumber gelombang itu kan, the wave sources, the beginning there, that's and the distance between the two sources is the A. Okay, then secondly is the X line. Okay, the X is the distance between one antinode and another antinode. And if we recap what we learned the last time, antinode is a line, antinode is a place where constructive interference happens. Okay, where crest meets crest or trough meets trough. Okay, and stuff like that lah. And the opposite of an antinode line is a node line. So a node is a place where destructive interference happens. So all this you've seen. And then the distance from where we count the A to where we count the X, okay, that distance in between them is the distance D. Okay, and from there, we have already formed the formula X equals to lambda equals to AX over D. Now, if I put Kochi all this, okay, and then actually this question is a little bit wrong lah. Okay, it's not actually write an equation this one in terms of X lah. It's actually express X. Okay, express X in terms of lambda. That means we want to change this one so that we will get X equals to yada 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 yada. Okay, and so what we will get is X equals to lambda D over A. Okay, and so we want to use this formula to see how each of this, the wavelength, the distance between the D and the X, A and the X, and the distance between the two sources. We want to see how this tree affects the distance between the two antinodes. Okay, that's what we want to do in today's class now. So the first thing that we're going to look at is we're going to look at the coherent sources. We want to look at how we change this is going to affect this. Okay, so that's the first one. Let's take a look at our name list alphabetically. We're going to start with Alvin. Okay, we're going to start with Alvin, question number 1, and then the next person, question number 2, question number 3, and so on and so forth. So everybody, please pay attention to your name in the name list. Not everybody is here, obviously. Okay, so take a look at the name list in the list of Google Meet participants. We're going to start with Alvin. Okay, so question number 1. This is number 3, right? Number 3 in your module. So the distance between the two coherent sources. So you look at this distance is big, and you look at this distance is small. Take a look at the value of X. Okay, Alvin, compare the distance A, please.
The distance between the two sources, diagram 1.58A is bigger than diagram 1.58B.
Okay, very good. So A is bigger than B lah. This distance is much bigger than this distance. Okay, next person, compare the distance X, please.
The distance X between two consecutive nodal lines in diagram 1.5.8A is smaller than in diagram 1.5.8B.
Okay, excellent. So A is less than B. Now, notice over here that this particular diagram, they are using the nodal lines from one nodal line to another nodal line. And that's totally fine. Okay, and that's totally fine. As long as you are aware of which distance you are connecting it. Okay, it cannot be from the node to the antinode. That one is wrong. It must be from node to node or from antinode to antinode. Okay, so good answer. All right, state the relationship between A and X, please. What does this graph apa ni gambar raja? Okay, tell us about the relationship between A and X. Next person.
The smaller the distance between two coherent sources, the greater the distance between the two consecutive nodal lines.
Okay, very good. Okay, so we have, okay, I know it's inversely proportional, but we don't write this. So we find that A and X are opposite to one another. Okay, let's look back at the formula. X is here and A is here. So when A increases, X will decrease. Okay, or when A decreases, okay, X will increase. So actually, if you look at the formula also tells us that kind of relationship. Okay, since X is on top and A is at the bottom, so they are actually inversely proportional. When one is bigger, the other one is smaller. When one is smaller, the other one is bigger. Okay, so yes, the Gamma Raja helps us, but we also have to remember that actually the formula also helps us to remember the relationship. Okay, so remember this formula especially. Lambda equals to AX over D, and then remember to change it to lambda X equals to lambda D over A lah, so that you can listen. Okay, state two other physical quantity that needs to be fixed in to ensure this relationship is correct. Next person.
Wavelength and frequency.
Okay. Not just frequency. Take a look at the formula. If this and this are relating to one another, so wavelength is one of the things that must be fixed. The other one is the D. Okay, the D, which is what's the D? Distance between the sources and the what is this D already? Oh no, it's too early in the morning. Anyway, the D lah. Okay, so this is the good thing about this formula. The formula actually tells us a lot of information. If the one in circle, if these two are relating to one another, therefore these two must be fixed. Okay, and you will find that that is the same for number 4 and number 5. There are two things that are relating to one another, so the other two things are fixed. Okay, and so the graph of X against A, okay, will look like this because it's inversely proportional. One is bigger, one is smaller. So the shape of the graph will look like this. Okay, so remember the shape of the inversely proportional graph. One is bigger, one is smaller. All right, good. Let's move on to the next one. Now we're going to talk about wavelength. Okay, I'm going to draw this here again. X equals to lambda D over A. Okay, now if you take a look, this one and this one are now relating to one another. Okay, they are the ones that we are finding out the relation. Okay, let's talk about the wavelength, please. Next person.
The wavelength of diagram 1.5.9 is greater than diagram 1.5.9b.
Okay. Good morning. So A is greater than B. Okay, yeah, no problem. Okay, thanks. Thanks for even being here. Okay, compare the frequency. Interesting. Okay, frequency. Next person. So
The frequency in diagram 1.5.9a is smaller than in diagram 1.5.9b.
Okay, very good. So A is smaller than B. Now, this is a very, very important thing. So just now, and I believe this was Chloe, just now, Chloe mentioned that the two things that should be fixed are the wavelength and the frequency. Okay. Now, the reason why I didn't really want to accept frequency is because when you change the wavelength, and this is the unique thing about waves, when you change the wavelength, you also change the frequency. When you change the frequency, you also change the wavelength. Okay, and the other interesting thing, and we will see this actually at the end of this chapter, is that wavelength and frequency, they are in opposition to one another. If a wave has a very big frequency, means the frequency is very high, the wavelength is very small. The waves are very near to one another. Okay, and if the frequency is very low, okay, sorry, frequency is very low, then we find that the wavelengths are much bigger. Okay, so they are like in opposition. If high wavelength, low frequency. Okay, low wavelength, high frequency. Okay, so that relationship is a very important thing that you should carry with you all the way until Form 5. Because even in Form 5, we're going to look at this again. Okay, so remember this, the relationship between wavelength is always in opposition to one another. Okay, compare the distance x, please, now. The next person. Okay, you find that A is bigger than B. Okay, it'd be so nice to hear your voice, Ivers, but okay, fine. Anyway, next person, state the relationship between lambda and f. Let's talk about the frequency first. Okay. Oh, I actually mentioned this. Okay, fine. Go ahead, Joey.
The smaller the frequency, the bigger the wavelength.
Okay, the smaller the frequency, the bigger the wavelength. Now, the good thing about this is that you can change it the other way also. If you want to say the smaller the wavelength, the bigger the frequency, also correct. Okay, so this is a very unique relationship. They can change one another. And it's totally fine to put one in front and then the other one behind. Okay, totally no problem. Good. State the relationship between the wavelength and the x. Next person. Joey is who? No. Just now was Joey.
Yes.
Oh, yeah, it was Joey. Sorry. Okay, now next person, please. State the relationship between lambda and x. You find that the smaller the wavelength, when the wavelength becomes smaller, the x also becomes smaller. Fine? When the wavelength is bigger, the x also becomes bigger. See, this is a bigger x. This is a smaller x. Okay? So actually it is the bigger the wavelength, the bigger the x. Yeah, you can, at this stage, you don't have to really say it in full. Just say lambda and x. But it's actually, one is big, the other one is big. One is small, the other one is small. Okay? Careful, Junie. What has happened to Junie? Oh, no. Okay, next person. State two other physical quantity that needs to be fixed. Next person. Aaron. No, Kahao.
Distance of A and B.
Okay, distance of A and B. Okay, again, coming back to our formula, x equals to lambda d over A. So the one that is now being related is lambda and x. So therefore, d and A must be fixed. Okay, d and A must be fixed. Okay, so the graph of x against lambda will look like this, because it's directly proportional. Okay, so x against lambda will look like this, a directly proportional graph. Just to remind you, this is an inversely proportional graph, and this is a directly proportional. Okay, directly proportional means one is bigger, the other one also increase. If one increase, the other one increase. Okay, next person. Now we're going to talk about d and x. Okay, so let's talk about this, d and x. So now I'm circling these two. So you know already. One time you see the formula, you already know which one must be fixed. Okay, Meryl, what is the relationship between d and x?
The bigger the D, the bigger the X.
Okay, the bigger the d, the bigger the x. The further you are away, okay, and this one got no gambar aja lah, unfortunately. Oh, sorry, here. Okay, if the x is, if your d is small here, from A to here is small, you find that the x is nearer. But if your d is bigger, this gambar raja is not really very helpful, but the idea is there lah. Okay, the bigger the d, okay, the bigger the x. Okay, what is the two other physical quantity that needs to be fixed to ensure that this relationship is correct? Next person.
A and lambda.
Yeah, okay, it will be A and lambda. Now again, since this is a directly proportional graph, so the graph will be a straight line that starts from the origin. Okay, so sometimes it helps us to understand that when the relationship is directly proportional, when something is bigger, the other one is also bigger, right? Okay, it helps us to know what kind of graph it will be. We don't actually have to do the experiment in order to be able to predict the kind of graph that will happen now. We know that directly proportional, oh, okay, the graph starts from origin, is a straight line. If it is inversely proportional, the graph looks like a swollen knee, something like that lah. Okay. So this is, oh sorry, this is in a nutshell. Okay, in a nutshell, when these two are related, this one is fixed. Okay, again coming back to this formula. Okay, again coming back to this formula. So the three factors that affect the interference pattern. Okay, the three factors that affect the interference pattern are all found in this formula. These are the three factors that affect the interference pattern, which is the wavelength, the distance from the sources to the to the place where you measure the X, okay, and also the distance between the two sources. Each of these affect how far the one node is to another, how far the antinode is to another. Okay, so this relationship and these factors, it needs to be remembered, and it's very easily remembered because you have the formula over there. Okay, I hope this helps. All right, let's take a look at the next one, which is the interference patterns for light wave. So far we've seen water wave. Okay, balik we see water wave, water wave, water wave, water wave. Okay, which is this lah. Okay, we've seen this water wave, and oh sorry. Okay, so we see this pattern in water wave, everything in water wave lah, water wave, water wave, water wave, water wave. So now we want to see what interference looks like in light waves. Okay, which is why we are looking at this next part lah. Now, this is how a normal experiment will look like lah. Okay, so we will have a red color light source, so like a red laser. Okay, and then we will shine it on this thing called a double slit. Okay, a double slit is essentially, let's see if you look at it from the top, it is like this lah. There's two slits over here. Okay, it's a double slit. Okay, and this double slit, okay, the double slit over here actually acts as, okay, this is two coherent sources. Okay, and actually if you played with the interactive, okay, if you played around with the interactive and you changed it to light, you probably would have seen this lah. Okay, so you find that this is what the interference pattern looks like. Okay, and this slit over here actually is a very familiar thing. We've seen this in the last subtopic. And remember what happens to light now? Okay, what happens to the wave after it passes through a slit? Let's say it's a single slit. What is this phenomenon called? Anybody? What is diffraction? Okay, it's called diffraction. Okay, so if it is a single slit, if a wave, doesn't matter whether it's a water, light, or sound wave, if it passes through a single slit, okay, we call it diffraction. But if the light wave passes through two slits, okay, obviously, first of all, every time it passes through a slit, it will diffract. So over here, okay, is diffraction. Okay, now tell me, what is the pattern of the wave after it passes through a slit? What does this plane wave become? What shape does it become?
Circular.
Yeah, it becomes circular shape. So it will look like this. Right? And then on this side, the second one also will look like this. And do you see that because both of them have turned into circular shape, therefore they will start interacting with one another. Sorry, not interacting. They will start superposing with one another. And we find that after they pass through the slit is where interference happens. Okay, sorry, my horrendous writing. Yeah, okay. So in order, so it's quite amazing. You have this one single wave, and then because it passes through two slits, okay, the two slits act as the two coherent sources. And after diffraction, the pattern of the wave becomes circular, and the two circular waves will interfere with one another. Okay, and they will form this kind of pattern. This kind of pattern is very chantik lah, kan? See, it's even more. Remember the diffraction pattern we saw in diffraction? The center is very tebal, and then the next one is like starts to get more and more nipis. And, but for interference, it's quite nicely arranged. Okay, and you find that over here, this is, okay, obviously the center is what? This is antinodal, okay, because it is bright. Okay, the dark patterns show you nodes, because that's where destructive interference happens. You don't get a red color light, you get a black color light, because the red and the crest and the trough will cancel each other out. So that's why the color also will gonna cancel out. Okay, so we can use this pattern to calculate the distance x. Okay, take a look at this gambar raja, everybody. In your module, take a look at this gambar raja. Okay, first of all, let me ask you, how long is this y? Anybody? Can anybody tell me? Look at the ruler inside your this one. Okay, how long is this y? Y equals to? Anybody?
7.2.
Okay, 7.2 cm. Okay, so remember, x is in between one to another, one antinode to another antinode. Okay, so I try to think about this. If this whole thing is 7.2, how much is, sorry, how much is this? How long is this? Just one set. Sorry.
3.6.
No, not 3.6. How do you get 3.6? 7.2 divided by 2.
No. Oh, yeah.
7.2 divided by 2. No, we can't divide by 2 because how many patterns of this are there? 1, 2, 3, 4. There are 4 sets of x's. And remember, x is, sorry, I need to change color. Everything is red color now. Okay, so x is one antinode to another antinode. So this is 1x. And this antinode to this antinode is another x. So we have altogether 4 sets of x's, kan? Oh, so if 4 sets of x's, okay, 4 sets of x's is equals to, how much was it just now? 7.2. If 4 sets of x's is 7.2, how much is 1 set of x?
1.8.
Yeah, okay, it will be 1.8. And this is how we calculate, this is how we can use to calculate okay, the value of the x. But we need to know how many sets. Okay, I tell you all, everybody makes this mistake one. How many sets? Okay, each set, one set, one set, one set, one set. Then you divide the total length by the number of sets. Okay, that's why we divide by 4 and we get 1.8. Okay, and so, when we do this experiment, you change this one okay, change the A, you change the D, and you will get this okay, you get this kind of pattern. Okay, and so this experiment is repeated with different size of gap, okay, 0.5 and 1.0, and then you get a different distance. Now let's come back to this. X equals to lambda D over A. Okay, let's compare these two first. This one has a different D. Okay, so what do you expect this X to be? Will it also increase, or will it remain the same, or will it decrease? What do you think? If the D gets bigger, what happens to the X?
Also bigger.
Okay, it will also increase. So you expect to see that. Now let's compare this. This one is the D is the same, but the A is different. Okay, so what do you expect to see in these two? Will this X, the first one and the second one, which X will be bigger? The first or the second one?
Number 1.
Number 1, because the A is smaller. Okay, it's a very important thing. So let's go to the questions first. I'm going to come to this in a while. Let's go to the questions first. So the red light from a laser pen is also known as a monochromatic light. Okay, now what is meant by monochromatic light? So monochromatic light, this is a definition. Okay, monochromatic light is a light that only has one color, alias, one wavelength. Okay, so the words mono means one. Okay, like monopoly and mono stereo. No, mono. You know, like if you listen to music, right, you have stereo. Stereo means both sides can hear. If you have just mono, means you can only hear one side. So mono means one. Chromatic, okay, chromatic is another word for color. So monochromatic means one color light. Okay, so what is meant by monochromatic light is light with literally one color, alias one wavelength. Okay, now this is a general question lah, and I'm sure that everybody can answer this, but I'm going to ask the next person, who I don't know who is the next person. Who is the next person now? Okay, Iril. Sorry, Bernardine, your mic is on. Okay, Iril, can you tell me the 7 colors of the rainbow? What is the first color of the rainbow? Okay, after red is? Are you going to type out all the 7 colors out? Okay, fine. After red is? Okay, orange. After orange is? Okay, yellow. After yellow is? You know, I have to keep switching back and forth because they're typing. Okay, after yellow is what? Where got blue? No, it's not blue. It's not yet blue. Blue is the 5th one. Between yellow and blue is what? Yeah, it's green. Okay. So red, orange, yellow, green, blue. The other 2? Purple is the last one. This is very interesting. Purple is the last one. Sorry, purple. Okay, there's one more in between blue and purple. Poor Ariel. He has to type out all the 7 colors of the rainbow. Yeah, okay, it's indigo. Okay, now I don't know how you remember this, but last time in the past, how I remember this was in Malay lah. So merah, jingga, kuning, hijau, biru, indigo, ungu. Okay, so it will be, the way I remembered it was Michael Jackson kena hantar balik India Utara. That's how I remembered it lah. Yeah, and I don't know why they had to say Michael Jackson in India Utara lah, but anyway, that's how I remembered it lah. Okay, anyway, however you remember the colors of the rainbow, this is the interesting thing. So each color has its own wavelength, which we will look at the end of this chapter. Red has a different wavelength, orange has a different wavelength, yellow has a different wavelength, green, blue, indigo, and purple, all the 7 colors of the rainbow that we can see with our eyes, okay, have different wavelengths. And only when all these wavelengths combine, okay, is where we get, who knows? When all the 7 colors of the rainbow combine, what color do we get? Do you know?
Black.
No, we don't get black. It's very interesting that you would say black, though. Huh? You don't know? Sorry?
White.
You know? Okay, yeah, we will get the color white. Do you know that there's no such thing as individually the color white and individually the color black? Sorry, I'm about to blow your mind, but let's just think about this. White is actually a combination now of the 7 colors of the rainbow. That is the real white color. So when you see the sunlight now, okay, like now it's very sunny. So when you see the sunlight now, what is actually entering your eyes is all the 7 colors of the rainbow combined. Okay, and yeah, it's a pretty amazing thing. Now, black on the other hand, okay, there is, this is also another mind-blowing fact. There is no such thing as the color black in terms of science. Okay, in physics or in science, there is no such thing as the color black. Black is just the absence of white. That means when there is no color, the only thing you're left with is black. Okay, so you cannot say that. I know all the artists are like, wow, Sir Marcus is preaching, is teaching us like boom. Okay, it's true. Okay, the darkness, black is actually the absence of white. When there is no light, then you are only left with dark. Just like, you remember when we were doing heat, I said there's no such thing as cold. Cold is just what? The absence of heat. When there is no heat, then you're left with cold. You can create fire, and you can create heat, but you cannot create cold. You just have to take away the heat in order for the situation to be cold. Same thing with light and dark. You can produce light. You manipulate the 7 colors of the rainbow, and you can produce light, but you cannot produce black. And okay, fine. Let's not talk about black light lah. Okay, I know that there is such thing as a black light, but again, even black light is just taking away black light is literally they're just absorbing the white color out. They're absorbing all the 7 colors of the rainbow, so that the only thing that you can see is darkness. Okay, when you think about it, it's so mind-blowing. You're like, yeah, the only way to be able to create darkness is to take away the light. So actually, there's no such thing as darkness. There's no such thing as black. Okay, there's no such thing. You cannot create black. You can only take away the white, and then you're left with the black. That's it. Okay, so like no hocus pocus. There's no magic, like boom, darkness. No, just take away the light. You turn off the light, and it becomes dark. You turn on the light, and it becomes bright. Okay? You don't create the darkness. You can create the light. You just can't create the darkness. Okay, anyway, mind-blowing fact for today. Correct. When RGB hues are the highest, it becomes white. And when the RGB hues are the lowest, yes, exactly, that's true. I guess people who, if you letter and if you have an iPad and you use Procreate now, you will see this very often. Okay, really, there's no such thing as black. Of course, all the artists will say, wow, this Marcus is teaching nonsense, bad. But in science, it's just that, okay? Black is just the absence of white. Okay, so describe the interference pattern. Okay, so we see this is the interference pattern. Okay, and the pattern is described as follows. The bright and the dark lines, they alternate and they are uniform. And this is the single difference between diffraction and interference. Remember diffraction, the center one is very, very long. And it's very not uniform, because the further it is from the center, okay, dia menjadi semakin nipis. But in interference, it's very uniform, very nicely tersusun. Okay, pop, 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 macam tu. Okay, there is no, okay, the rate in the center over here is longer than the rate over here. No, actually it's all same. They are alternate and they are uniform. Okay, so let's watch a couple of videos to see this interference of light, okay, happening now, because we cannot do it in the lab, right? Okay, so let's watch a couple of videos now.
Okay, so I'm going to try and demonstrate to you a practice.
Oh, sorry.
Okay, so I'm going to try and demonstrate to you a practical experiment called Young's double slits, named after a bloke called Young, who did loads of really cool physics. And this experiment uses 2 slits, as the name suggests. And this is really an amazing experiment, and you've got to do it yourself to really appreciate it. But I want to take you through it with this video first. If you're in my class, then you're going to do it next lesson yourself. We've got enough for you to do this experiment in pairs. So what does it involve? It involves this, which is a spirit level that's got a laser in it. So if I point that at the wall there, hopefully you can see it's a red laser. It's a nice low power laser that's going to be safe for us to use. Young did this hundreds of years ago, so he didn't have lasers, but they make our life easier, as you will see. We've got this thing here, which is a collection of double slits. So if you look really closely, you can probably see 4 slits in this slide. If I hold it up to maybe a white background, see it more clearly. Each of those things that you can see there, oh no, that's lovely, that's focused really nicely. So you can see that each of those things that look like one slit is actually a pair of slits. And the ones on the right are quite far apart, and the ones on the left are really close together. So these are double slits. What happens when the light passes through these 2 slits is that it spreads out. So when light passes through a narrow gap, it spreads out, it diffracts. And then the light coming from each of those 2 slits can interfere. So I'm going to shine the laser light through. I'm going to use the leftmost pair of slits because that's going to work best.
Okay. Sorry, let me talk about this. So what he's doing now here is he's showing you different A. You know, A is the source with the distance between the two sources. Okay, and so this distance here is 0.25 millimeters. We can't even imagine 1 millimeter. Imagine 0.25 millimeters. That's how near they are to each other. And if you remember, the reason why it has to be small is, okay, let's come back to the formula. X equals to lambda d over A. The smaller the A, the better the interference pattern, the more clear it will be. So we are expecting to see this. The one with this slit, okay, is going to show a further interference pattern compared to this slit. Okay, let's be aware of this. Right, continuing.
So I'm going to shine this laser through a double slit, and then all the way over there, I'm not sure if you can see it, is a screen. It's a long way away, and you'll find out why that is shortly. So here we go. I'm going to turn the lights off. I'm going to turn the laser on, and I'm going to direct the laser through two of the slits. So the laser light is going through a double slit, two slits very close to each other. All the way down there on the screen, you might just see some red. Now, actually, let me show you what it looks like without the double slit. Without the double slit, it looks like a dot. Okay, let's go back. Now, I've put a double slit in the way. So the laser light is passing through both of those slits. It's spreading out, it's diffracting. But when it gets over here, you get this very interesting pattern of bright and dark fringes. So it goes bright, then dark, then bright, then dark, then bright, then dark, and so on. So this is a two-slit interference pattern of light. Now, if you're in my class, we've already done this with other things. We've done this with sound. So we had two sources of sound, same frequency, playing the same pitch. And we walked past them and we noticed that in some places the sound was loud and in some places it was really quiet. I also tried to demonstrate it with ripples on a pond. The Veritasium video has got a really good video of that, where you can clearly see some bits where the water ripples are bigger and some places where the water ripples are smaller. So here it is. This is the two-slit diffraction pattern that Young observed. Now, often in textbooks you will see, you might see a photo of it like this, but often you will see this represented graphically as an intensity plot. So if I take the middle of it.
Okay, sorry, I'm going to stop here because dia tidak berapa kaitan sudah. So we find that you can actually do this experiment also. You can see a very brief pattern or you can see a very rough pattern. But you need to have something very nippies. So actually in the book, they say use 2 fingers. Okay, then so the slit over there. So if you want to have interference, you use 3 fingers. And then you have a gap over here and you have another gap over here, right? So the gap is very small. But in this particular demonstration, they use 3 pencil leads. Okay, so actually you can do this if you want at home, just to see how the interference pattern looks like. But you must have a laser, and the laser has to be a 1-color laser. Don't use a white color laser. Okay, use the the laser that you, if you have a cat, the laser that you use to catch out the cat the cat will run here and there. Right? I suppose that's why this guy's video is influenced by Philip the cat. Anyway, if you're able to do this, and if you use the pencil lead or use your finger, you should be able to see something like this, a pattern such as this. But what these guys are doing, they're using the double slits. Okay, our lab actually has these double slits. Okay, our school lab. Of course, the problem is getting back to school. But if not, actually, if you want to try this, take the pencil lead and then shine the laser through all the 3 leads. You should be able to see a certain interference pattern over there. But what we know is that the interference pattern is alternating bright, dark, and it is uniform. Okay, it's not like diffraction. Diffraction center very big and then the rest all becomes very small. Interference, it becomes very uniform. Okay, so again, the same thing, lambda, AX, and D. Okay, since now we are talking about light waves, okay, and so this light experiment is actually made famous by this guy called Thomas Young. Okay, Young's formula. So actually, this formula lambda equals to AX over D is actually known as Young's formula. Okay, lambda is the wavelength. A is the distance between the two slits. Originally, for water waves, I say is what? Two coherent sources, makan. Okay, but it's still the same thing lah. Okay, again, as I said, it's better to remember what the A looks like rather than to remember what it means like in words lah. Okay, because different, water waves have a different meaning. Light waves have a different meaning. Sound waves have a different meaning. Although actually they're the same meaning, just the words are different, so they're complicated. D is the distance between the double slits, okay, and the screen. Let's say you have a screen over here, like in the experiment just now. Okay, so this distance over here is the D. This is the A. Oh, sorry, A kecil. And then remember, X is the distance between two consecutive bright lights. Two consecutive bright lights means, what do you think this is? Are these antinodes or nodes? Anybody? Bright lights.
NT.
Okay, they are antinodes. Okay, they are antinodes because bright lights are observed when there is constructive interference. Okay, again, the reason why I wanted to go slow with this subtopic, because all these words okay, need some time to get used to. Okay, let's do this number 4. So we have the A is 0.5. Okay, this one is 2.0, and we have already calculated this just now. Remember, this was how much? 7.2 kaitu. And then we divide it by 4 and we get 1.8. Okay, can you use the formula lambda equals to AX over D? Calculate the D for me, please. Calculate the lambda for me, please. But everyone, be careful. This is millimeter, and this is meter. So we have to change this into meter. We have to change this into meter. How do we change millimeter to meter? What do we need to do?
Divide by 1000.
Okay, divide by 1000. Okay, atau darab 10 kuasa negatif 3. Either way also can lah. Okay, calculate first please. Use this formula, calculate the lambda for me and tell me how much it is. Your brain is not working already. The next person is Chen He, so I want Chen He to answer this.
7.2 times 10 to the power of negative 7.
7.2 times 10 to the power of negative 7 meters lah kan. Okay, sorry. 7.2 times 10 to the power negative 7 meters. Let's take a look and see. Looks correct to me. No, 4.5. How do you get 7.2? Did everybody else also get 7.2? 4.5 times 10 negative 7. Did the rest of you get this?
Yes.
Oh.
Yes.
Okay. Chenny, please figure out where you went wrong with this. Okay. All right. I'm going to move on to the next one. We're running out of time. So Y is the distance between 11 fringes. Okay. So there is 11 fringes in here, 1.4 cm. Okay. So when we calculate this, we get X equals to 1.4 millimeters. Let's do this exercise again, everybody. Lambda equals to AX over D. This is the A, this is the D, and this is the X. Okay, remember to change this millimeter into meter first. Okay, and then give me the answer for this. Okay, Trevor is the next person. So Trevor, please. Everybody also count now, but please, Trevor, give me the answer.
7 times 10 to 7 times 10 to negative. Wait.
7 times 10 to the power of?
Negative 7.
Negative 7 meters. Okay, I think this is correct. Okay, 7 times 10 to the power negative 7. So actually the calculation is quite easy. Okay, just multiply, divide by everything. Just you have to make sure that the units are the same. Everything must change to meter. You cannot have 1 millimeter and then the other 1 millimeter. Cannot. Everything must be the same. Okay, let's have the last three people. Vion, Wong Yixwan, and sorry, Alvin again. The last three questions. What will happen to the fringes of the screen? Means the X. What will happen to the X when the D is decreased? Okay, I want Vion for this. When the red light of the laser pointer is replaced by the blue light. Okay, I want Wong Yixwan for this. Okay, and then distance between the double slit A is increased. Did I miss anybody today? Wow, everybody who is answer is here. Okay, sorry, Alvin, we have to go with you again. Alvin is like, okay, Vion, what happens to the X if the D is decreased?
Decrease.
Okay, the D will, the X will decrease lah. Okay, remember everybody, D is directly proportional to X. So if D decrease, X also will decrease. Okay, Wong, if we change the red to the blue color light?
Suddenly forgot of which color is the bigger wavelength.
Okay. Let's talk about colors of the rainbow again. Okay, red, orange, green, Michael Jackson, yellow, red, orange, yellow, green, hantar balik blue, indigo, and purple. Okay, red has the highest wavelength. Purple has the lowest wavelength. Okay, so that means blue has a smaller wavelength than red color. Okay, so that means you're actually decreasing the wavelength. So what happens to the X?
Decreases.
Okay, it will decrease. This is a very important thing. The colors of the rainbow are actually arranged in decreasing wavelength order. Okay, and next year you will study that it is also arranged in increasing frequency order. From red to purple is decreasing wavelength and increasing frequency. It becomes so important in Form 5 lah. Okay, but in Form 4 we are very focused on wavelength only. All right, last one, Elvin. The distance between the double slit A is increased. What happens to the X? If you increase the A,
increase.
Okay, it will also decrease. Okay, because it is inversely proportional. So I hope that today, okay, well, by looking at the factors and looking at the light wave punya interference pattern, okay, I hope that you remember that, yes, for calculation purposes, okay, we use lambda equals to AX over D. This is Young's formula. But in order to understand or to know the relationship between the X, we have to change it to become X equals to lambda D over A. Just manipulate this formula and change it to like this so that you can see what is going to increase and decrease. Okay, how the X is going to increase or decrease. Okay, so next Monday, we're going to look at this. Okay, we're going to look at sound wave, and then we're going to answer a couple of questions. Okay, so what I would like you to do, okay, over the weekend, hold on. Okay, what I would like you to do over the weekend is to look at activity 6. Okay, activity 6 in your module, okay, and answer question everything except for number 4, because we haven't done sound wave yet. Okay, but you should be able to answer 1, 2, 3, 5, and 6, and it's only one formula, which is the lambda equals to AX over D formula. Okay, so just do that in preparation for Monday.